This is page 288, chapter 12. Back to Daniel. Everybody go? Okay. All right, number 1. We got the picture below. It says, a block slides down a frictionless ramp and a sphere rolls without sliding down a ramp of the same angle. The block and sphere have the same mass, start from rest at point A, and descend through point B. In the descent, is the work done by the block's weight on the block greater than, less than, or the same as the work done by the sphere's weight on the sphere? They're the same. Very good. Think of your most basic work formula, force times distance. They have the same weight, that is the same downward force, and they travel the same downward distance. So good. At B, which object has more translational kinetic energy? Basically meaning linear kinetic energy. Yes. The block will have more linear kinetic energy because the sphere also, some of the sphere's kinetic energy is divided into what else? The sphere also has translational kinetic energy, but it also has what kind of kinetic energy? Rotational. So since the sphere is also rotating, that takes up some of its kinetic energy. So very good. The cube would have more translational kinetic energy. And which would have more speed down the ramp?
The cube?
Yeah, for the same reason. Because the cube has more translational kinetic energy. Okay, number 3 is next. Back to Zach. A cannonball rolls down an incline without sliding. If the roll is now repeated with an incline that is less steep, but of the same height as the first incline, RA, the ball's time to reach the bottom and translational kinetic energy at the bottom greater than, less than, or the same as previously. Okay, so first part, so we have the steep slope, then the less steep slope, ball's going down, it's rolling, not sliding. The ball's time to reach the bottom. Where is that going to be faster? Steep or less steep?
Steep.
Steep, okay. And then therefore it's it's translational kinetic energy at the bottom, regardless of the fact that the steep one gets there first. By the time they both get to the bottom, what would you say about the translational kinetic energy?
The less steep one would be. Well, what do you mean by translational line?
Like linear speed, linear kinetic energy.
Then, no, the steep one.
The steep one gets there first. Which one has more potential energy?
Are they the same?
They're the same. They start at the same height. Steep one does get there first. But by the time the less steep one gets there, they're both spinning. They're both at the bottom, so they would both have the same translational energy. Yeah, it was similar to something else we did. Not the easiest one, because you would need to know that they are rotating the same, but it would be the same. All right, number 4, Thomas. A solid brass cylinder and a solid wood cylinder have the same radius and mass. If they have the same radius, Connor, how could the brass and the wood have the same mass? They're the same size disc. What would have to be true about the wood cylinder? Good question. Or it kind of tells us in the next just little bit there. They maybe both have this radius, but the brass cylinder is like this long, the wood one's going to have to be longer. Okay. But as we know from our moment of inertia formula, that does not matter. The height of the disc does not matter. Okay, anyway. So they're released together from rest and they roll down an incline. A, which cylinder reaches the bottom first, or do they tie, Thomas? Very good. They would tie. They have the same moment of inertia. They tie. All right, now D says the wood cylinder is then shortened to match the length of the brass cylinder. And the brass cylinder is drilled out along its axis to match the mass. So we've really made the wood cylinder and like a hoop out of the brass cylinder. But they still have the same mass. Which one wins the race now? Very good. The solid wood, because the hoop has more moment of inertia. It has more resistance to change, so it would start out slower. Yeah, we did that one, for example. I believe that was a day when my audio was off. That's all right. Not bitter. All right, number 6. I guess you can still tell that. Back to Wes. Position vector r of a particle relative to a certain point has magnitude 3 meters, and the force on the particle has a magnitude of 4 newtons. What is the angle between the directions of r and f if the magnitude associated with the torque, we're doing r cross f, equals 0? Good. 180 or 0. All right, what if they equal 12? Yeah, that's when they are perpendicular, which is what we want in the cross product. Or 270, very good. All right, that was number 6. Number 7. Brandon. And there's one of these, I at least remember this one on the test. There are a few of these on the test, but. All right, number 7 shows a particle moving at constant velocity v and 5 points with their xy coordinates. Rank the points according to the magnitude of the angular momentum of the particle measured about them, greatest first. So even though this object is not rotating in a circle, we could still calculate its angular momentum about any given point, as long as we remember that formula. Remember the angular momentum formula for a point mass, Brandon? Or anybody? The angular momentum formula for point mass. M part's right. Oh, you're giving me the rotational inertia. That is mr squared, sorry. I'm looking for the L.
Oh, that's...
There you go. And again, not V cross R, R cross V. Okay, so they're all the same mass, the same particle. So you're looking for the greatest R cross V, Brandon. Good. And just remember, again, it's a cross product. So even though R, would technically be like this, I really only care about the perpendicular part of that. So I'm just looking for the perpendicular component to this vector. I know this vector is over here, but I can put vectors wherever I want. So That's what I care about. Okay, so anyway, B is right first. Then what? They are pretty similar. They actually do tie. They are both, what, about 2 coordinates away? C's 2 above, D's 2 below. Okay, so C and D tie, and then what about A and E? They should be 0 because the R and the V are not perpendicular. They are parallel. All right, very good. Next is 10. Back to Connor. The following gives the angular momentum of a particle in 4 situations. I guess they use, if it's a particle, they use like a little l instead of a big L. I don't know, that just occurred to me. Anyway, so we have, equations 1, 2, 3, and 4. In which situation is the net torque on the particle 0, positive, and constant? And does anyone remember the relationship there between torque and angular momentum? Perhaps you remember this formula as well. Force is the derivative of momentum, so correspondingly torque is the derivative of angular momentum. So yeah, we're just looking at derivatives. Okay, so what are we on? I lost my spot. How did I flip my page? Sorry. Okay, yes. So 10A. Equation 3 is 0, correct. All right, how about positive and constant? Good. 1, because that would just be 3. And then negative and increasing in magnitude. Very good. 2, because that would be negative 12t. And then negative and decreasing in magnitude. Yeah, it's got to be our last one. That's got a t to the negative 2 in it when you do the derivative. All right, 2 more. 12, 14. All right, back to Erica, number 12. A rhinoceros beetle rides the rim of a disc rotating like a merry-go-round counterclockwise. All right, if it then walks along the rim in the direction of the rotation, will the following increase, decrease, remain the same? So you got your turntable, spinning, spinning, spinning. Now the beetle walks the same way that it's spinning. What will happen to the angular momentum of the system? Good. Momentum should always be conserved. At least the momentum of the system should be conserved. So it stays the same. What happens to the angular momentum and also the velocity of the beetle? Good. So the angular momentum would also increase because it's related to the speed. Okay, but what happens to the angular momentum and velocity of the disk? Yeah, exactly. It's got to decrease. You can think about its little feet almost pushing it backwards. If it's gaining speed, the disk has to compensate for that by slowing down. Part D, if the beetle walks in the opposite direction, then everything just be opposite. Switch your answers. But, except for A, angular momentum is still conserved. Okay, and last, Daniel, number 14. This one's kind of similar to Brandon's. All right, the figure below shows an overhead view of a rectangular slab that can spin like a merry-go-round about its center. Also shown are 7 paths along which wads of bubblegum can be thrown, which is gross, all with the same speed and mass, to stick to the stationary slab. Rank the paths according to the angular speed that the slab and gum will have after the gum sticks, greatest first. So imagine the gum hitting the slab at all these random angles and distances away from the rotation point. Which one will cause the greatest speed?
5.
No. Will 5 cause it to spin at all?
No.
No. So we're looking for perpendicular things, ideally. Let's think our angular momentum, mr cross v. We're going to have the greatest angular momentum, and therefore the greatest speed, when r cross v is the biggest.
Four.
4, there you go. They're all the same v, so you're basically looking for the greatest perpendicular r to that v. So 4 is the biggest. Okay, let's actually do the 0 ones. Which ones are not going to cause it to rotate at all, besides 5?
6.
No, 6 will make it spin. So we're looking for,
2.
good, 2. You know, if you draw a line from the rotation point to that impact point, that radius is parallel to number 2. Okay, so 5, 2 is not going to make it spin, and one more.
3.
Good, 3 is also not going to make it spin. All right, so back to the greatest. We know 4 is the greatest. What then would be next?
6.
Okay, which actually also ties
The 7.
the 7, yep. They're just making it spin different ways. All right, and then last,
1.
number 1. Good. For which pass will the angular momentum of the slab and gum about O be negative? So it's a little right-hand rule question. Which one's going to make it spin, basically so your thumb is into the page, negative? Looks like there are 3 of them. Good, 1.
2.
No, 2's not making a spin.
Forget.
Okay, so 1.
1.
Again, right-hand rule, you're taking your right hand, you're pointing your fingers in the direction of R. The direction of R means from O to, whatever number we're going to. And then crossing your fingers the way the velocity points. So 1 makes it spin. How about number 4? Or, sorry, 1 makes it spin negatively. How about number 4? Is that going to be a positive or negative?
Negative.
Good, negative. R is towards the corner. Then I kind of curl my fingers up and left. So that's negative. And then we got 6 and 7. Which one of those would be negative? 7. There you go. Questions, comments, concerns, statements? That was the last one, right? Yes.